Hi everyone. Today we're going to be simplifying radicals. I suspect that we need to refresh your memory a little bit. You did, most of you, in 8th grade, some perfect squares and square roots. And so I need to make sure that you recall that and that you're familiar with the symbols. A radical is really the inverse operation of exponents. So squaring something, the power of 2, and the square root of something, like this square root of 16 here at the bottom, those are inverse operations. They undo each other, just like addition and subtraction undo each other, right? When we're solving an equation, or multiplication and division, that's called inverse operations. The power of something and that root are inverse operations. So in this case, the power of 3, which is called cubing something, and the cubed root, where there's that little 3 inside of the radical symbol, are inverse operations. And look, they undo each other. 2 to the power of 3 equals 8. And the opposite of that, if I do the cubed root of 8, I get back to 2. All right, so most of the time you see square root, and that's what we're going to focus on. Notice with square root, like this one, there is no little index. You see how the little number inside of the check mark part of the radical symbol? That's called the index. If there's no number written, you assume it's 2, which is square root. And what it's asking you is what times itself 2 times gives you the number under the radical. The number under the radical is called the radicand. So we have the index, which is the little number in the hook, and it's how many times something gets multiplied by itself to give you the radicand. The radical symbol is that sort of check mark with a top, and it looks a little bit like the division symbol you first learned how to do long division with. Okay? Let's look at how to do some examples simplifying radicals. You did, back in 8th grade, perfect squares, something like the square root of 25. And you said to yourself, what times itself gives me 25? Well, 5 times itself is 25. So the square root of 25 is 5, because 5 times 5 is 25. So the problem now is that these aren't perfect squares, and you're going to be asked to simplify them. So you're going to make them with the smallest number under the radical as possible. You're going to take out anything you can. I find that there are a couple of ways to do this, but I would prefer to show you one way that works for everything. So notice when we did the square root of 25, what we really looked for is a pair of numbers that gave me 25 when I multiplied them. And then our answer was that number once instead of twice. We're going to use that. I want you to do what's called a prime factor tree for the number under the radical, the radicand. I'll show you what I mean. What two numbers multiply to give you 18? There's a few choices, and honestly, it doesn't matter which ones you pick as long as they multiply to give you 18. How about 9 times 2? You'll see in class you could have used 6 times 3, and this comes out the same. All right, so a factor tree uses branches. And anytime the number at the bottom of a branch could be broken down into factors other than 1 in itself, we keep going. We're interested in the bottoms of the branches being as simplified as possible. 9 is 3 times 3, right? And I can't go any farther because I'll have ones. 3, the only way to get 3 is 3 times 1. You don't go that far. All right, I'm only interested in the bottoms of the branches. So I'm looking here, here, and here. Not here, because that's up the branch. Anytime you have a pair of numbers, a match, circle them. I have 3s. I'm circling it because look, remember the before? All right. And anytime anything is left that doesn't pair up, that doesn't match, I want you to put a box around it. Because now here's the trick. To simplify a radical, anything that pairs up, we bring one of those outside the radical. And anything that doesn't pair up, and we box them so we don't lose them, stays under the radical. And guess what? That's it. So the factoring part, you have to get used to. But pairs come out in front of the radical, and anything that doesn't pair up stays under the radical. This 3 square root 2 is the simplified form of the square root of 18. Let's try it with another one. The square root of 125. We start our factor tree. Any two numbers that multiply to 125. You might not know off the top of your head. You might have to use your Desmos calculator or any calculator to try a few things. Try 2, try 3, try 4, try 5. See what works. 5, because this ends in 5, I can tell. 5 divides evenly in. So you do 125 divided by 5. And when you do that, you get 25. All right. Well, 5 is only 5 times 1. And I told you, you're not going that far. Once you get to 1 times the number itself, you stop. You don't go that far. But 25 is 5 times 5, isn't it? All right, bottoms of the branches only. We're not counting this. You circle any pairs. You put a box around anything that doesn't pair up. Anything that is circled comes out of the radical. You take one of the numbers for each pair. And anything left over, anything that doesn't pair up, stays under the radical. And you're done. 5 square root 5 is the simplified form of the square root of 125. I want you to try the next couple on your own. I get it. It takes some practice. Give it a shot. Pause the video, try them, and then come back and check your work. All right, check your work. Final answer is what you're interested in, because I recognize that you might have started your factor tree different, but I got to tell you, the things that you got at the bottom of the branches might be in a different order, but they have to be the same. So you should have at the bottom of your branches, no matter how you started, gotten 2 3s, 2 2s, and then an extra 2 that didn't pair up. And for number 4, you should have gotten, no matter where you started, at the bottom of your branches, a pair of 3s, a pair of 2s, and a 5 that didn't pair up. Everything that pairs up, 1 comes out for each pair. So the pair of 3s, a 3 came out. A pair of 2s, a 2 came out. That 2 that I put in a box didn't pair up, stays under the radical. If you have more than one thing come out of the radical, you multiply them together. That's the rule. Multiply them together, you get 6. The 2 that didn't pair up, it stays there under the radical. For number 4, same thing. 1 3 came out for that pair, 1 2 came out for that pair, and the 5 that didn't pair up stayed under the radical. Since more than one thing came out of the radical, I multiply them back together, and I have 6 square root 5 as the simplified version of square root of 180. I don't want you to worry. We're going to practice more of these in class, and I promise you it's going to click and it'll come together. But I want to make sure that you see what to do with letters, variables. And I got to tell you, this is even easier than with numbers. Anytime you have an exponent for a variable, how many does that tell you they're being multiplied together? Like x to the power of 3 meant x times x times x, right? 3 times. Okay, so we're going to use that. If you didn't know it before, you know it now. Any variable to a power means that many of that variable multiplied together. So b to the 7th means b times itself 7 times. 1, 2, 3, 4, 5, 6, 7. Now, I want you to circle pairs. Just like we did with the factor tree, circle pairs because we're looking for groups of 2. Remember, this is square root. We're looking for groups of 2. Anything that doesn't pair up, put a box around it. All right, so anything that's a pair, we pull out as 1, right? Just like we did with numbers. 1b for this pair, 1b for this pair, 1b for this pair. Anything that doesn't pair up goes back under the radical. Wait, but we already said b times b times b could be written as b to the 3rd. That tells me I had 3 pairs of b's and 1 b that didn't pair up. Let's do another one. There's 11 m's, all right? Write out the 11 m's, circle the pairs, put a box around anything that doesn't pair up, and write it out the way I did in the last one. Let's see if you can finish it. Okay, check it out. How'd you do? I wrote out my 11 m's. I circled pairs of m's. I had 1 m for each pair, so there was 5 pairs, so 5 m's outside the radical. 1 m that didn't pair up, that stays under the radical. And instead of leaving all those m's written out separately, there were 5 pairs. And so you see how you could sort of just skip to that. Now it'll take some practice, but after a while you won't have to write out the letters that many times because you know you're looking for pairs. So you can think to yourself, how many groups of 2 could I get out of 11? 2 goes into 11 5 times and 1 left over. There it is. Right? 2 pairs. 2 goes into 7 3 times evenly, and there's 1 left over. You will get good at this. Give it a chance. We're going to practice more in class. I want you to try these on your own. Pause the video and then come back and check your work. How'd you do? Did you notice that there were no leftovers? Everything paired up. That means there's no more radical. These were actually perfect squares. It looks funny because those exponents aren't perfect squares. But when we're looking at variables, we're looking at how many there are. Pairs come out. 1 pair, 1x. 4 pairs, 4 x's. 3 pairs, 3 x's. All right, in class, we're going to practice problems that have letters, variables, and numbers. You can do this. I'll see you in class.